Okay, welcome back, everybody. All right, so today we're going to talk about Fourier series, and we're going to build up to Fourier transforms and representing functions in terms of orthogonal function spaces. So a couple of things I want to do first are the following. I want to talk about the kinds of additional PDEs that we could think about based on what we know now that are either going to be on homework 3 or on the midterm. Okay? So something that will definitely be on the homework is to derive Laplace's equation on a disk. Okay? The basic idea here is that you can take and write down x equals r cos theta, y equals r sine theta, and you can derive a 2D Laplace's equation purely in polar coordinates, r and theta. And you could solve this Laplace's equation on a disk if you had the temperature distribution at some fixed radius and temperature. Okay? So deriving the 2D Laplace's equation, I mean, you can Google this so you know what the right answer is. You can Google, like, what is 2D Laplace's equation in polar coordinates? But I want you to derive it from the 2D Cartesian Laplace's equation with partials and this expression. And then I might ask you to solve this problem, so the Laplace's equation in polar coordinates with a boundary condition. So what would be the equilibrium temperature distribution inside of a disk with this boundary condition? You would use separation of variables, but you would do it in polar coordinates now. Okay, that's the kind of thing I might ask. Other kinds of things I might ask would be looking back at the rectangular thermal equilibrium problem. So again, we're dealing with Laplace's equation. And we had some boundary condition, some temperature on the left side, and then 0, 0, 0. Equals u, equals u, equals u. What would be a simple way of changing this problem up? What are some other boundary conditions that we have for heat equations or for Laplace equations? Insulated. So an easy way to change this problem is to have insulated top and bottom. Okay, that's another kind of question that I would either ask on the third homework or on the midterm exam. So you would essentially rework this exact problem, but with insulated boundary conditions. I actually think it was easier this way. Something like that was easier. Okay, that's another kind of equation that I might ask you. I might also give you a guitar string question. So essentially, you have this guitar string, you pluck it, and you have certain differential equation utt equals ux, x plus, there's some constant here. And I might have you solve this equation using separation of variables. Okay, so separation of variables, Laplace's equation, different coordinate systems, different boundary conditions are all fair game. If I gave you something like this, where it was a new type of physics that I had never told you about before, then I would be obligated to tell you the equation and the boundary conditions that I expect you to use. So it doesn't really matter what the physics is. You would get a system of equations, and the physics would only help you interpret, what is physically reasonable or not. Okay, there's of course also going to be complex analysis and integrals and all kinds of other stuff on the exam. Okay, this one's going to be a little more difficult than the exams in last quarter, possibly, because I'm trying to get you ready for the qualifying exams, and so I want you to be solving more real-world problems. Okay, these are all the kinds of problems you would actually solve in research, and that's what you need to be able to do on quals. Okay, any questions about this? This is the last I'm going to talk about midterm before the midterm. I haven't written the midterm yet. Okay, how many of you feel moderately prepared for the midterm or more? Greater than or equal to moderate? How many of you feel less than moderately prepared? Okay, well, there's a few days left. Things I would do, I would go over the basic things that you know about complex analysis and complex integrals. You should be able to deal with complex variables and complex numbers. You should be able to take like complex number to some power or log of a complex number, things like that. You should be able to do Taylor series with complex numbers in them, and you should be able to take complex integrals, contour integrals, and use things like Cauchy integral formula, Cauchy Gorisov theorem, things like that to change your integrals and do what you need to do. And then we'll have some kind of PDEs on the exam. Okay, great. So that's it for midterm stuff. Okay, so the next 3 or 4 lectures are going to be about Fourier series and Fourier transforms. And I'm going to start off using the Fourier series as kind of an aside. So we've been moving ahead in complex variables and then in partial differential equations. Now we're going to talk a little bit about how we represent functions in general. Okay, so when I have differential equations like ut equals alpha squared uxx, or utt equals uxx, or uxx plus uyy equals 0, right? If I have any of these partial differential equations, the basic idea is that u is some function. Right? The solution of my partial differential equation is a function. It's a function of time and space, or just 2 spatial variables. Okay? So u is a function of some variables. And what we would like to know is what are some alternative ways of representing functions in general? Okay? What we have are, we represent functions in some coordinate system. So we represent functions in some kind of a coordinate system. So what are your favorite coordinate systems that you use all the time? Okay, Cartesian, right? So x and y. What are some other ones? Polar, r and theta, some other ones. Spherical. R, phi, and theta, some other ones. Sorry? Quaternions. We'll just skip that one. Cylindrical, and so on. So there's lots of specialized coordinate systems that we use to write equations. And why do we choose some of these over other coordinate systems? Okay. Ease of representation of the equations, ease of computation of the equations. Maybe sometimes when I write down my physics in these coordinate systems, maybe some of the variables drop out. When would that happen? When would I have variables just drop out of an equation? When it's symmetric in some way, if there's some kind of a symmetry, right? So for example, well, there's tons and tons of examples, right? Like gravitation is symmetric. It only depends on the radius. It doesn't depend on either of the other 2 variables. Okay, and if I have a reduction in the number of variables, then I have a reduction in the complexity of my solution. Okay, so this is essentially called dimensionality reduction or symmetry reduction, and it's been one of the most powerful tools used in physics since physics and math were invented. People were taking complicated problems, writing them in funny coordinate systems so that they simplified, and then solving them in those weird coordinate systems. Okay? So Fourier transforms, Laplace transforms are no different. They're just a new coordinate system where we can write our function where the physics, the equations, and the solutions simplify. Okay? So Fourier and Laplace, they're basically very similar. So Fourier transforms allow us to write our functions in a new coordinate system. And they allow us to write our functions in a new coordinate system where they become dramatically simpler. Okay? And we're going to be writing these in terms of sines and cosines. So I'm going to talk more about this later. We're going to get a clearer picture of what I mean. But what I want to do is build this up with a lot of examples and a little bit of theory to motivate why we care about Fourier series and Fourier transforms in the first place. Okay, so how many of you have seen Fourier series before? Fourier transforms? Okay, how many have never seen one or either? Okay, good. So Fourier series are great. What they do is they allow us to take most functions that we care about and write them as an infinite sum of sine waves of higher and higher frequencies. Okay? So if our function f of x is 2 pi periodic, we're going to break all of these conditions later, and piecewise smooth. So what does it mean for a function to be 2 pi periodic? Just means it repeats after every 2 pi. Okay, so if I have x and f of x, I can do anything I want between 0 and 2 pi, but at 0 and 2 pi, my function better have the same value, and it better repeat every 2 pi forever. Okay? So basically that means that f of x plus 2 pi equals f of x for every single x you can name, for all x. Okay, so if f is 2 pi periodic and it's piecewise smooth, so this thing can even be nasty. It can have it can even have jumps as long as it repeats every 4 pi. Okay, so this thing can be piecewise discontinuous. Then we're going to be able to write f as this infinite sum of sine waves of higher and higher frequencies. Okay, then f of x, our function, we're going to say that this almost exactly equals our Fourier series function. So this new function is my Fourier series, and it basically equals my function. And that equals some constant plus an infinite series for all integers n equals 1, 2, 3, up to infinity of an cos nx plus bn sine nx. Okay, an and bn and a naught are just numbers. Okay, and an and bn have their own formulas for how we get them. Okay, so an is equal to 1 over pi integral minus pi to pi of f of x cos nx dx, and bn equals 1 over pi integral minus pi to pi of f of x sine nx dx. Okay, I'll let this just sink in for a little bit. Maybe I should box this. This is pretty important. I didn't have to integrate from minus pi to pi. That's just a choice I made. I could have integrated from 0 to 2 pi, or 1 to 1 plus 2 pi, or 14 to 14 plus 2 pi. It doesn't matter. This thing's 2 pi periodic. So any domain that is length 2 pi and continuous in x is a fine integration bound. Okay? I'm just choosing minus pi to pi. I'm choosing this for a reason that will become clear later, which is minus pi to pi allows me to evaluate whether or not my function is even or odd. Okay, if I integrate from 0 to 2 pi, it's not super clear if this function is even or odd until I look at what happens from minus pi to pi. And then I can see if it's symmetric or anti-symmetric. Okay. So minus pi to pi is kind of conventional. This is what a lot of people do. You're going to see me jumping back and forth from minus pi to pi to 0 to 2 pi. It doesn't matter. Okay. So the basic idea is that if my function f is reasonably well behaved, then I can represent it as a sum of sines and cosines, and the frequencies of these sines and cosines start at frequency 1, and they go all the way up to frequency infinity. And I have to add up all of these things, and then I get an almost perfect representation of my function. Okay, so I've been going back and forth about what the right order to explain things is, because I don't want to confuse you before you have the right foundation to know more about Fourier series, but I also want to tell you the full story. Okay? So I think I'm going to tell you the full story first. This function f of x equals f of my Fourier series f of x. This is only, they're not strictly speaking equal. They're kind of equal. Okay, and I'm going to tell you what kind of equal means. So these are equal in a norm that I define on my function spaces. So these are equal in an integral sense, which means that the integral of, so f of x minus my Fourier series of x, there's something called a 2 norm on functions. How many of you have some basic idea of what a 2 norm on a function is? Okay, I want to explain this to you. This is going to become super important. It's not complicated at all. It's really, really simple. So just like we have vectors and we can define the distance of vectors, right? What we do is we add up the squares of the sum of the squares of the component differences and then take the square roots. That's the norm of a vector. Well, I'm telling you that all of these functions are living in an infinite dimensional vector space, and so they also have a norm, a difference between these two vectors. Every function has a length, and the difference between two functions also has a length. And if the distance between these two functions is 0, then we say that they're basically the same function. And the way we define that distance is we say, well, this is equal to the integral over the domain I care about, minus pi to pi, of this function squared, of f minus my Fourier series squared dx. And this equals 0. That's what I mean by these two functions being equal. What I mean is that these two functions are infinitesimally close to each other in function space. For all intents and purposes, in this inner product, in this norm, they're 0 distance apart. They're the same function. Now, what that means is that if I have some function, now why am I making all of this fuss about infinite dimensional vector spaces? Why don't I just say that the functions are equal at all points x? Because this basically would only be true if my functions were equal at all points x, right? Okay, so let's say that I have my okay, so let's say that this is my function that's 2 pi periodic. So if this function, this Fourier series, has to be basically the same at all of the points in my domain. But at this discontinuity here, it doesn't know which point to be. So something crazy happens right there in my Fourier series. This red curve is my Fourier series. And so as long as this discontinuity only happens at a few places, this difference still only integrates up to 0. This doesn't happen over any appreciable dx. So what this means is that my function and my Fourier series agree at every point where my function is smooth over the entire domain, and it's going to disagree at all points where f is discontinuous. But as long as I have, countably many, as long as I have, 100 or 1,000 or 1,000,000 of these discontinuities, as long as I don't have a whole patch that's discontinuous, then these disagreements between my Fourier series and my regular function still add up to 0. Those differences are confined to infinitesimal dx's. Okay, this is a little bit weird, but I want to tell you the full story. So anyway, we have this definition of a length of a function, and these two functions are equal as long as the length of the distance vector is also equal to 0. Okay, it's a little weird. We're going to get some better intuition for how this works later. If you have any questions, please ask.
Are there other senses of equality that are notable that we've come across?
There are other senses of equality. This is called the L2 integral norm. This is by far the most used integral norm in all of physics. This is what you use in quantum mechanics and general relativity and all kinds of physics, and this is the most common one. The L2 integral norm was invented to handle functions like this one that had these finite occasional nastinesses occurring, because you can still say in what sense my solution agrees with the original function as long as these discontinuities are relegated to very, very small, finitely many occurrences. So this L2 integral norm is very nice and smoothing. There are L1 integral norms, L3, L4, L4 thirds, L pi integral norms. There's a whole family, a continuum of integral norms that are each useful in their own context. And there's completely different norms that don't involve integrals of functions. Yeah?
What's an example of a system where this kind of trajectory would be seen?
Like in the heat equation, let's say I had two bars. This one's hot, and this one's cold. And at time 5, I butt them up against each other. Okay, or let's say I take my guitar string and I pull it back and I let it go. So I have this initial condition where it starts and then it evolves. Like there's other, so we kind of approximate things like my finger plucking a string as discontinuities that would then impulsively force my system. So we need to be able to, that's both great questions. You need to be able to handle these, and the L2 integral norm is kind of the most common way of handling these discontinuities. Yeah.
So, based on the math, does that mean that if there is a discontinuity and the function is evaluated there to be a positive value, that there should be a negative value which corresponds to that? Does that make sense?
Sorry, so if I take this difference and it's a positive number?
Yeah, so when you say that it is equal to 0, does that mean that there is another discontinuity which has the opposing sign so that it cancels out before you evaluate it?
No, so this discontinuity is a finite disagreement between these two. It's a real positive disagreement, but it's multiplied by something that we're taking the limit as it goes to 0. So this L2, L stands for Lebesgue. There was this really smart, how do you spell Lebesgue? It's Lebesgue. So this guy, Lebesgue, was trying to figure out how you integrate functions that have discontinuities. He was much more concerned with a different discontinuity, like the Dirac delta discontinuity, where you have something like a Gaussian, but where its height is infinite and its width is infinitesimal. Okay, so you take the limit of a zero variance Gaussian, you get this delta function. And so what he argued is that you actually can integrate these functions that might even be infinite valued over one tiny, tiny location if you... So we're used to adding up our integrals using horizontally, vertical rectangles that we add up horizontally. And he decided, why can't I just do it like a layer cake? Why can't I add up vertical slices that are stacked, horizontal slices that are stacked vertically? I can add them up that way. And then I can handle this infinite valued function. I can just take the limit and see if everything cancels, and I get 1 when I integrate this delta function. So Lebesgue introduced these different kinds of integrals that handle a few finite discontinuities. This is called the Lebesgue integral. And these L2 integrals allow us to handle things that have discontinuities. So this L2 integral you can do using the normal Riemann way. And if you add up all of the differences between these two things, if I look at my distance, f minus f Fourier series, I have something that's 0, 0, 0, 0, finite, 0, 0, 0, 0, 0. And if I add up all of these little rectangles, I get 0, 0, and 5 times 0. Dx is 0 here. So as long as I have, as long as these really are discontinuities that happen at an exact x location, then the integral of this error is still 0, because it has 0 width in x. 0. So we call that this has no measure on the x-axis. If you tried to measure the width of this delta function with a tape measure, it would have 0 measure. Okay? So Lebesgue was really smart. He came up with this notion of measure, funky integrals to handle discontinuities and infinite values, and he created this entire family of integral norms, the LP integral norms. And we're going to use the L2 for our functions. Okay, so just one last thing before we get into a much more concrete example again. So L2 of A comma B. This is a notation that we introduced. This means this is an entire family of functions. This is a set of functions, right? The real numbers is a set of numbers. The integers is a set of numbers. There's infinitely many of them. This is a set of functions. These are a set of functions that are square integrable on the domain x inside A to B. So this is a whole family, a huge family of integrals, of functions. Basically, every function that you can name almost is in this family, almost every function. And if I had a function f in this space of functions, then it would satisfy the property that my integral from A to B of f of x squared is a finite number. So if something is square integral, it just means that its square integrated doesn't blow up to infinity. Almost every function that is nice and happy that we're used to thinking of, sines, cosines, exponentials, all of these functions, they're square integrable on most domains. A good example of a function that's not square integrable is f of x. This is a counterexample. F of x equals 1 over x on 0 to 2. This is definitely not square integrable on the domain 0 to 2 because this would blow up to infinity. Right? This integral is not finite. Ooh, maybe it is actually. Nope, it's not. definitely not. So this is not square integrable, but a sine, a cosine, so I'll say this is A and this is B. Any function that's bounded between A and B is square integrable. The only things that aren't are things that blow up to infinity in a catastrophic way. Okay, that's enough function space stuff. I want to do some MATLAB, and I want to go back to the concrete example of a Fourier series. So I gave you a function that's 2 pi periodic. Now I'm going to generalize this. We're going to say that they don't have to be 2 pi periodic. They could just be L periodic. So this also works for functions that are L periodic. This L is just a length. It's not L like Lebesgue's name. This is just a length, L periodic. So my Fourier series is still equal to some constant plus an infinite sum, n equals 1 to infinity, of a constant an times cos. But now my cos has to have period of L. Okay? So these are going to be harmonics of the 0 to L length. So these are going to be cosines of 2 pi nx over L plus bn times sine of 2 pi nx over L. Right, I have this 2 pi over L here because I'm saying that my function is periodic between 0 and L. So my sines and cosines have to start and stop at 0 and L. These have to be the nodes of my sines and cosines. And so that's why I have this 2 pi over L factor here. And an is also pretty simple. It's just 2 over L integral 0 to L of my function times cos 2 pi nx over L. And bn is 2 over L integral 0 to L f of x sine of all this stuff, 2 pi n x over L. So this should start looking pretty familiar. This is exactly what we had in the last example in class on Friday, where we had the heat equation and we had some thermal, some temperature distribution on the right-hand side of the rectangle, f of y. And we were writing our function in terms of sines of different harmonics. Okay, so we were looking at half of this series last time, just the sine half of the series last time with the heat equation. Okay, so I want to code this up in MATLAB and give you some examples of what this looks like. Okay, these are all things we can do, right? We can integrate a function times cosine of any frequency we like in MATLAB over any domain we like, and we can add up functions and plot them. Okay. Okay, so what we're going to do, the first thing, I'm just going to create some function that we're going to approximate using Fourier series. Okay. So I'm going to define a dx equals some small number. My length, I'm just going to make it equal to 1. The x is going to be dx in x to L. Okay, so I have a dx, I have a domain from 0 to L, and I have some spatial variable that goes in dx's up to L. And we're going to say that my function is equal to 1s of the size of x. So what does that make my function? 1. F of x equals 1. This is just a big vector of 1s. Right? We can just plot this. Plot x by f. 1. Okay. But what I want to do now is I want to say that the first half of f, the first half of the values in f, I want to set equal to 0. Okay, so now this thing steps up from 0 to 1. So this is a step function. It's a pretty poor way of drawing this. Maybe I can axis negative 0.5 to 1.5, negative 0.5 to 1.5 probably will work. Okay, that's my step function. Yeah?
Is there a reason why I started the x vector at dx instead of 0?
I started it at dx. There are two reasons. I want this thing to have length of 200, not 201. This vector, like I just don't want it to be, if it starts at 0, then I have a hard time remembering how long it is. It's always, L divided by dx plus 1. The other reason I don't want to start at 0 is because I would end up double counting 0 because my function should be 2 pi periodic. This one's not. I totally lied. This works for non-periodic functions, but if my function really was 2 pi periodic, then I would have already captured the left value at x equals 0 because I'm including x equals L. So you don't want to kind of double count the boundaries. Just pick one and include it and don't include the other one. Okay. All right, that looks good. All right, so now what we're going to do is we're going to build up our Fourier series, and we're going to start plotting the Fourier series as we increase the number n. Okay, so our Fourier series is equal to 0 size of x. We're going to start with just zeros, and then we're going to add, cosines and sines of higher and higher frequencies and see how it converges. Okay, the last thing I need to do is say that I have this constant a naught over 2 out front, and a naught is equal to this integral where cosine of 2 pi 0 x over L, where n is 0. And what's cosine of 0? 1, and it's 1 for the entire domain, for all of these x's. Okay, so the a naught coefficient I get by taking 2 divided by the length of my domain times the sum of my function times a vector of 1s of size x times dx. This is just a fancy way of saying I'm integrating my function times cos of 0 dx. Okay, so for m equals 1 to 100, maybe I'll just say okay, so we start with this constant. Our Fourier series is a naught over 2 plus a bunch of sines and cosines. So for k equals 1 to 100, I'm going to, maybe I'll say n equals 1 to 100. I'll say AK and AN and BN equals. So I'm going to compute my coefficients AN and BN, and then I'm going to add AN sine of 2 pi n over L plus BN cos 2 pi sine over L. Okay, so what are my coefficients AN and BN? I'm never going to remember these, and I can't see them from the board.
2 over L.
Okay, 2 over L times. Times, I'm integrating, so I'm going to add up a bunch of stuff. And what am I adding up? Okay, I'm going to term-wise multiply my function by what? Cos of 2 pi nx over L. Right? I'm integrating f of x with cosine of 2 pi nx over L for n1, n2, n3, n4, da da da. Okay. And I better multiply by dx. So I don't want to just add up all these numbers. There's a dx. Okay, and bn is similar, 2 divided by L sum f dot times sine of 2 pi nx divided by L dot dx. Okay. And the last part is my Fourier series is going to be growing. I'm going to add more sine waves to it. And so I'm going to add this current sine wave, which is an times cos 2 pi n x divided by L plus bn times sine 2 pi n x divided by L. Okay, I think that'll work. Sorry?
It says there's an error on line 15 and 16.
Oh, good. Thank you. Cool. Okay, good. So now we have this growing function. We're going to add up 100 sine waves. And I've already plotted the function that I want. And so now down here, I'm going to hold on and plot the function I have in red dashes. Let's hope this works. I don't have a backup. All right, so it works. You can see that my red dash line almost perfectly captures this black line. It's very, very good. Almost looks too good. It's really, really, really good. Let's say I have 10 modes here. Okay, if I just add up the first 10 sines and cosines, this is what I get. Not perfect. Interesting, though. So the basic idea is that I can add up more and more sines and cosines until I build up this shape. And if I add up enough, if I add up infinitely many sines and cosines, then eventually this function will completely agree, except at these discontinuities. And you notice that the weirdest stuff is happening at the discontinuities. It's happening at the point where you go from 0 to 1. And you can also think of the fact that my function is not periodic. That's another discontinuity. Okay, like this is just discontinuously going back down to 0. And so I have this other big discontinuity that's symmetric over here. Okay, so first, any questions about this code? Maybe I should show you the code. Is it pretty clear what we're doing? In terms of, like, there's some formula for getting A's and B's. And every time I get a new A and B, I get a new, coefficient times sine plus coefficient times cosine that I add to my series. This series goes on forever. There's some things I didn't tell you. For example, why is it that this approximation just gets better and better and better the more n that I include, the more modes that I include? I call these sines and cosines modes. Why does this approximation just get better the more sines and cosines that I include? It's not obvious. I'll explain it more later. So let's make a big for loop here. So for m equals 1 to 100, so these are the mode numbers. We're going to start with 1 mode approximation, then 2 mode, then 3 mode, then 4 mode. Okay. This might work. And eventually it becomes perfect. Why does it become perfect? This is super weird. Why does the approximation become perfect with exactly 100 modes? I have an infinite series here. This is not a trick question.
200 increments.
Because I have exactly 200 increments, right? So this is a purely numerical artifact. There's still all that crazy shit going on. It's just that in this dx, it's exactly equal to the function value. Okay, so that's called aliasing. So all of these errors are being aliased out by my very, very clever choice of dx. But if I change my dx, now this is dangerous because I haven't actually tried this, but if I change my dx to 0.0001, I'm pretty sure that those won't go away as m goes to 100. I'm pretty sure I'll keep having some pretty bad disagreements between my functions. Yep, that's n equals 100. M equals 100. So you still get those disagreements when I have the resolution to see them. Okay? And these will only get kind of infinitesimally small as my number of modes goes to infinity. This phenomenon has a name where you get this big ringing. Does anyone know what this is called? Gibbs phenomenon. So this is called Gibbs phenomenon, where you get this high frequency ringing near sharp edges. This is the same Gibbs from physics. Pretty interesting. You could try any function here. This was just a function I cooked up. We could try, let me get rid of this craziness. So m equals 5 in increments of 5 to 100, maybe 2 in increments of 2 to 100. So let's say that our function f equals just sine of x. What's going to happen in this example?
Get it in one iteration.
Maybe. Let's see. Ooh. Nope, still takes a lot of iterations because sine of x is not periodic on 0 to 1. Okay, so let's try sine of x times 2 pi. Perfect. One iteration. I'm fighting with MATLAB here. So it got a perfect agreement in one iteration. There's one last cool function I think I can code up pretty quickly. Let me just grab it from over here. So this is a sawtooth function. Okay, big sawtooth function. Looks a little weird, but we're going to see how this does. Okay, we see that with very, very few iterations, this thing converges to the sawtooth pattern, which is really nasty, ill-behaved. Okay, there's so many interesting things we can do with this. We have a lot of choices in front of us, okay? So part of me wants to spend more time thinking about Fourier series because they're just cool. So for example, in this equation, is this an even or an odd function? Odd function, right? So if I pictured what would be happening back here, it would be kind of equal and opposite sine waves. So it's like anti-symmetric or skew-symmetric. And so if I looked at the coefficients an and bn, what would you expect to happen? I would expect that all of my a's are equal to 0, and the only non-zero terms are b's. Because I'm basically trying to approximate an odd function. I can only do it with my sines. I can't possibly do it with cosines, or else I'd have weird even function crap happening. So for odd functions, I can represent odd functions purely using sine series, Fourier sine transforms. And for even functions, I can exactly represent them with only the cosine terms, these Fourier cosine series. And for general nasty functions like that step function, then I actually would need both of them. Okay, for general functions, I need both sines and cosines. But for special even functions, I can get away with just cosine series. For special odd functions, I can get away with just sine series. This is really quite important because in the last lecture, we had a series that was just in terms of sine waves. But sine waves aren't enough. Sine waves are not complete. If we think about this vector space analogy, then each of these sine waves of different frequencies is a direction. Okay? But if I only have the sines alone, I only span the space of odd functions. If I just had my cosine directions alone, I would just be able to span the space of even functions. And the only way I can span the space of all possible functions is to have both sines and cosines. Okay, so in the next lecture, what we're going to look at, we're going to try more Fourier series. We're going to start looking at what these coefficient values look like, why they decay to 0, why this gets better and better with higher n. And we're going to generalize this to function spaces. Okay, thank you.